Okay, I want to take a look here at the homework for section 1-3. I'm going to start off here with number 1. So if a ball is thrown into the air with a velocity of 40 feet per second, so I'm just going to start writing things down. That's the velocity it's thrown into the air with. Its height in feet t seconds later is given by this equation, y equals 40t minus 16t squared. All right, so this is just telling us that if a ball is thrown up in the air with a certain speed, here's the position of the ball after a certain amount of time. So y is going to be the height in feet of the ball after t seconds. So for example, if t is 0, this is all 0. That means the height of the ball is 0. So it's 0 feet off the ground at t equals 0. If you look at it 1 second later, at t equals 1, this is going to be 40. And then this will be minus 16. So 40 minus 16, that's going to be what, 24? So it'll be 24 feet off the ground 1 second later. And so we have a model for what's going on. The questions, part A, excuse me, part A is to find the average velocity for the time period beginning when t equals 2 and lasting, and then there's multiple parts. So we want to look at what's going on. We want the average velocity at t equals 2, and then in the first part here, 0.5 seconds later. Okay, so let me try and explain what's going on here. This ball is doing something, right? If I were to draw a graph, this is a parabola, we know that. It opens down because we have a negative 16 in front of the t squared. We already looked at it, at t was 0, it was like this. And we know that the ball goes up and then it comes back down like this. Well, what they want us to look at is the average velocity between t equals 2. So I'm just going to put it down. I don't know if this is the right point, but here's t is 2. And they want us to look at between t is 2 and 0.5 seconds later, which would be 2.5. And so if we take this, we imagine there's some point on the graph here. That's supposed to be straight up, sorry. And then this one right here. They want us to find the average velocity on that little time interval. So the average velocity, remembering that velocity equals distance traveled divided by time. And in this case, the distance or the height of the object is given to us by this, y equals this. These are our y coordinates on top. Our distances are y coordinates divided by time, which are kind of like our x coordinates were. We're calling it t. Then this is really just y's, the difference in y's over the difference in the t's, which you should connect back to college algebra, is really just the slope of that secant line. So what we're asked for here in part A, part 1, is for the slope of that secant line. So I'm going to say the velocity is going to be equal to, all right, so we have to figure out what, I'll just put rise over run. So what's the rise? What's the difference in the y coordinates? Well, I need to first figure out what happens at 2. So let's take this right here, and I'm going to kind of rewrite it like a function. Y of t equals 40t minus 16t squared. When I'm looking at rise over run, what I want here is what's happening at y of 2.5. So what happens when I plug 2.5 into this? Subtract, I'm going to run out of room, sorry. I think I'll do it right here. So my velocity will be the y of 2.5 minus the height at 2, y of 2, over now the difference in these two. So 2.5 minus 2. All right, so I'm going to have to break out my calculator. And I'm going to first plug in 2.5 into this. So 40 times 2.5 minus 16 times 2.5 squared. Make sure I got that. It's 0. And just double check I got that. 40 times 2.5 minus 16 times 2.5. Yeah, it's 0. So this is 0 minus, now I plug in 2 into that. So 40 times 2 minus 16 times 2 squared 4. I get 16. And then over this is 0.5. So we should get negative 32 here. And this is a velocity, so feet per second. So my picture is not good, all right? I didn't know where the points were, but now that I kind of do know where they were, at 2.5, I'm at 0. So if I redraw this, kind of to give us, do right here. If I redraw my picture, we knew at 0 we were here. At 2.5, we're here. And at 2, we're up at 16. So I don't know. I still don't know exactly what it looks like, but this is okay. We wanted to find the slope of that, what we call secant line, which was the slope of the line connecting these 2 points. And that turned out to be negative 32 was that slope. So if you're looking just on this little time interval between t equals 2 and 2.5, the average velocity on that time interval was negative 32 feet per second. So that's part A, part 1. For part 2 of part A, they want a smaller time interval. They want you to look at, instead of 0.05, 0.01 seconds. So how does that change the picture? Well, instead of looking between 2 and 2.5, we're going to go between 2 and 2.1. So that's a different point somewhere up here. So all that changes here, we're still going to be looking at trying to find the average velocity. We're going to go 2.1 minus 2, and then, y of 2.1 minus y of 2 over 2.1 minus 2. And get our calculators out, do it again. What is your guess here? My guess is that this line will not be as steep negative. It's going to probably pitch up a little bit. So I doubt we're probably going to get a number that's smaller in magnitude than negative 32. So I go through, plug in 2.1 first. So plug in 2.1 in this, 40 times 2.1 minus 16 times 2.1 squared. I get 13.44 minus, now y of 2 we already know is 16. And then this is a little different too. We get 0.1. So let me compute the top first. We get negative 2.56 and then over 0.1, which is going to be negative 25.6 feet per second. So you can see that, you know, this other secant line like this will be less steep this way, negative slope, but it's still negative slope. And now we want to continue, and what we're doing, the important thing is we're looking at 2, we started at 2.5, we moved into 2.1, and now we're going to probably in part 3 go even closer. We're going to change this for part 3 to 0.05 seconds. So that changes this right here to 2.05, and then this one 2.05, and everything else stays the same. So we're kind of looking at t equals 2 as being kind of like the base point, and we're just moving closer and closer to it. So 40 times 2.05 minus 16 times 2.05 squared. 14.76 minus 16, that didn't change. This changes though, 0.05. And I'll do that real quick. Negative 24.8, okay. So remember, we started out when we were far away, it was negative 32. Then we moved in, it got a little smaller. Now we moved in. Now it's approaching, or it's getting close to negative 24. Let's see if we go even smaller. This will be the last one we do, because it's the last one they asked for. 0.01. So if I change this, 0.01, 0.01, like that, and I plug in all right. I get 15.78 or 758 something. Good enough. This changes to 0.01. Divided by, I get negative 24.16. Now we could keep going. I mean, we could get even closer than that. We could do 0.001 or 0.0001 or 0.00001 and try and figure out what's happening as you get really, really close to 2. The thing is, we know that we can't just look at what's happening at 2. If we do that, we put y of 2 minus y of 2 over 2 minus 2. You get 0 over 0. It doesn't make any sense. Now, I think I'm going to do this one just so you can get an idea here. I'm going to do this one on my calculator real quick. 40 times 2.1. So if I do this one in here and do all that stuff, I get negative 24.00016. Look, so it appears from all indications are that as I get closer and closer to 2, right, as I move closer and closer to 2 from this right side, that this slope is getting closer and closer to negative 24, which means that it makes sense that the speed of the object at 2 is probably negative 24, if it's possible to talk about the speed of an object at an instant in time. It looks like it would be really close to negative 24. So that's what we're trying to do here. We're trying to use this idea of creeping in towards a number to get an idea of what's happening at the instant. So for part B, it says estimate the instantaneous velocity when t is 2. So our estimate for what's happening at 2 is that the velocity would be negative 24 feet per second. I'm out of room here. Okay. All right. I hope that makes sense. Now, number 2 is the same exact thing. The only difference, and I'm not going to work out number 2, I'm going to let you do it yourself. The only difference is the way that they give you the information for setting up this part right here. Like, they give you a function, they give you an equation, and then they give you an interval of time. So I'll just write it down so you can see it here. So I'm not going to work this out, just want you to see it. So you've got this equation, this is number 2. Y equals 10t minus 1.86 t squared. And for part A, part 1, they give you 1, 2. So what that means is that you're going to be looking for the velocity, and I should put average below here so we know what we're talking about, not the instantaneous, but the average velocity will be this I'm going to turn it into a function, so I'm going to call it y of t. It'll be y of 2 minus y of 1 over 2 minus 1. So they give you the initial point 1, and then how far over we are. So on the number line, we're here at 1. This is kind of like our base point. Then we're going to start at 2. And then I imagine with the next parts, yeah, the next one will be 1, 1.5, so we'll move in. Then it'll be 1 and 1.1, so we'll move even closer. And you just repeat the process that we did in number 1. Okay, now number 3 is a lot different. There's a graph, and this is a little bit harder to do because I'm going to have to draw it first, but I will do it. Just bear with me. Remember that in YouTube you can play videos at a higher speed. It's in the bottom right hand corner. You should be able to adjust. All right, so let me draw this first. And this is going to be my best effort. Number 3. So we got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have at 3. Here's 2. Here's 4. Got this circle. Dot. Circle. I'm just looking because I want to make sure I'm as accurate as possible, but some information that looks like that's not important. So here's the graph. All right, now part A. They want you to find this thing. Now I need to have a better picture here. All right, let's start with this. We want to know the limit as x is approaching the value of 1 of this function. So this is the graph of f, right? These are x values. So what we do is we say, all right, I'm going to take a look at x equals 1. X equals 1 is right here. All right, and what I want to do is figure out what's happening to the y values of the function as I approach 1. So I'm just going to draw kind of a dotted line up here. It looks like up here at 2, right, is where what's happening. When you plug in 1, it looks like you're getting 2. But I'm not interested in what's happening exactly at 1. Since this is a limit, I'm looking at what happens as I get close to 1. So I'm going to draw a horizontal line here. Like this. Uh-oh. Hey, yeah, you have a meeting? No? Oh, hold on, let me mute. Okay, sorry about that. These homework videos I do in a little conference room, and I get interrupted sometimes. I apologize. Okay, so we are going to be looking at what happens as x approaches 1, and we're looking at the y value. So at 1 it was 2, but we're going to be approaching it. So we have to look at 2 different scenarios: the left side and the right side. If I am coming in on the left side of this function, walking along, as I am approaching an x value of 1. My y values are starting up here and they're starting to come down, and they are getting closer and closer to a y value of 2. So just imagine if you were to plug in a point a little to the left of 1 and go up, you would be just a little bit above 2. But as you got closer to 1, you'd get closer to 2 for the y value. So from the left, the function's value is approaching 2. Now on the other side of 1, on the right side, as I approach, I'm coming in, now as I'm coming into 1 from the right, my y values are below 2. But as I get closer and closer and closer. These y values are starting to get closer and closer to 2, but they're coming up from the bottom. So, you know, if I plug in something like this in here, I'm going to be, you know, like maybe 1.9. If I get even closer, I'm going to be maybe at 1.99. But at the end of the day, the closer I get, the closer the y values get to 2. So from the left side, it's getting close to 2. From the right side, it's getting close to 2. So the answer to this is just 2. That's somewhat obvious because there's nothing interesting happening at x equals 1. It's just a nice smooth curve. All right, for part B, this is a little different now. And this is really why we're here. It's why we're studying this. Is something like this. What happens is x approaches 3, then it has that little negative sign there. Now, the little negative sign on the top right-hand corner of the 3 means that you are going to be approaching from which side? Well, remember, on the x-axis, the negatives are on the left, the positives are on the right. So when you see the negative sign, that means you're going to be coming in from the left this way. So I need to first go to an x value of 3. Okay, and just imagine, okay, as I'm approaching this from the left side only, that's all I'm focusing on. So I must be to the left of 3. I need to find my function, which is right here. I need to start approaching 3. So not way out here. I need to be close to 3. So, you know, maybe around here. So what's happening? I'm kind of dipping down, and then I'm coming back up. So what y value am I getting close to? Well, it's getting close to this open circle. That open circle looks like it has a height of 1. So I go a little bit below 1, but then I start to come up and get closer to a y value of 1. Now, once I get to 3, I'm no longer here. I'm actually here, but that doesn't matter. That's what the limit's all about. It's just looking at what happens near a value of x, not at the value of x. So from the left, my y value, again, was approaching 1. Now, from the, or for part C, my guess is we're going to be coming in from the other side, yes. So what's the limit as x approaches 3 plus from the right side of the function? So now here's 3. And then I'm going to go to the right of 3, somewhere over here, and find my function. Here it is. And I'm going to start walking towards this x value of 3. So I'm moving along, moving along. My x values are getting closer, 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 closer. And as I get close to 3 on the right-hand side, what's the y value? Well, looks like it's up here, getting close to this, whatever this is. So this is what, 1, 2, 3, 4. So that's 4. So if I was over here, I'm below 4. But the closer I get to 3, the closer I get here to 4. So it looks like my y values are approaching 4. Now for part D, they're just going to want to know what the limit is as you approach 3. And they don't tell you left or right. Now this is critical. And there's a reason why they did this. Because in order for this limit to exist, if they don't tell you plus or minus, that means you have to check both. Like we did on this one. Remember I checked both sides? This means we have to check both sides, which we've done already. We checked the left side, we checked coming in from the left, we checked coming in from the right. But in order for this limit to exist, we need these two answers to be the same, and they're not. Okay, so what happens when I come in from the left is different than what happens when I come in from the right. Since those aren't the same, we say that this limit does not exist. And the shorthand we use for that, DNE, does not exist. All right, so I will, oh, there is one more thing they're asking, part E. They want to know what's f of 3. So you don't see a limit here, right? There's no LIM there. Since you don't see a limit, this is back to just college algebra. What's the function's value at 3? So go to 3, exactly at 3, look up. Do you see a dot somewhere? Yes, here. What's that value? 3. So done. All right. Now I'll let you do number 4 on your own. And I think 5 will also be something you can handle, hopefully. And that'll be it. So let me move on to number 6. All right, number 6, we want to sketch a graph. F of x equals, this is what we call piecewise function, 1 plus sine x, cosine x, sine x. We do this if x is less than 0. We do this one between 0 and pi, and then x greater than pi. There we go. All right, well, I'm going to draw a picture and then we'll answer some questions. So you took pre-cal, so you should be able to graph these. Let me do the easy ones first. Well, they're all kind of basic. This is the sine curve moved up 1, right? Just shifted up 1. And this is what we're going to do if x is less than 0. So here's x is 0. And so a normal sine curve would go like this, right? And then backwards it would be down and back up and like that. But we want to move it up 1. So here's 1, here's negative 1. And what I'll do is I'll draw what it would have been. Negative pi, negative 2 pi. May as well go over here and do the same thing. Pi, 2 pi. I hope you can see that okay. I know I wrote that really small. Pi, 2 pi, negative 2 pi. So a normal sine curve would go like this, right? You're going to go like this and then like this. And then backwards, the backside, I'm going to draw it dotted, would be something like this. Well, I went too high. You get the idea. But then we want to take that, we want to move it up 1. So it's going to look like this. That. And it'll actually come up to 2 now. All right, so this is the first part of the piecewise function. Okay, that right there is 1 plus sine x. And then notice that that's what it is if x is less than 0. By the way, it continues and it keeps going that way. That means that at 0, we want to put an open circle because it's not defined at 0, right? There's not a little line under there, so I leave it open here. Now the next curve is going to be the cosine curve, and it's cosine just between 0 and pi. So we know that cosine, normal cosine curve, is going to go, I don't know, should I draw this? That's your cosine curve, right? And we just want it between 0 and pi. So I'm going to cut it off here, like that, between 0 and pi. And notice the equal signs here. So at 0, we want to fill it in. And at pi, we want to fill it in down here at negative 1. And then finally, we have the sine curve. And the sine curve, oh, I do have another marker. The sine curve, we want just when x is bigger than pi. So remember, the sine curve would have come in here like this, would have been like this. Would have come in, would have gone like that, would have come in like this, right? But we only want it between after pi, so that would be from here on. Like this, like that. And it's going to continue forever. And because there's not an equal sign, I'm going to put an open hole there. Like that, that's it. And take this out. So this is the graph of the piecewise function. And it says, determine the values of a for which the limit exists. Okay, so take a look at this. This is a nice nice trig function, continuous. I shouldn't say continuous, we haven't talked about that yet. they want to know where the limits exist, all right? So like if I just picked a point over here and I said, hey, go up here, does the limit exist? Well, if you come in from the left and from the right, sure. I mean, you're going to go to the same place from the left and the right. There's really only one place on this entire graph that we have a problem. And so we notice that at pi, as we come in from the left and then we come in from the right, they're going to two different places. So I'm a little bit confused with the question because they want you to say where it does exist. And the limit exists everywhere except here. So what I'm going to do is I'm instead going to tell you where the limit does not exist. So at x equals pi, the limit as x approaches pi of the function does not exist. Otherwise, it does. So if I pick any value of x on this line, and I ask you to take the limit is going to exist. This is the only place where you're going to have a problem because you have a break in the graph. Okay, that's it. This was just a good exercise in drawing some trig functions, and then at the end we threw a little bit of the limit stuff in there just to make sure you understand what's going on. All right, moving along. Numbers 7, 8, 9, and 10 always give students problems. And what I'll do is I'll pick one of the more challenging ones out of those and do one. They say in the instructions, sketch the graph of an example of a function f that satisfies these conditions. So I think what I'll do is number 10, and I'll let you figure out 7, 8, and 9. So let me write down the conditions. We need the limit as x approaches 0 from the left of the function to be equal to 2. We need the limit as x approaches 0 from the right of the function to be equal to 0. We need the limit as x approaches 4 from the left of the function to be equal to 3. We need the limit as x approaches 4 from the right of the function to be 0. And we need f of 0 to be 2. And we need f of 4 to be 1. All right. Now keep in mind, everybody's answer to this might look different, all right? Because all you have to do is graph a function that satisfies these conditions. Keep in mind, a function still has to pass the vertical line test, all right? So we want to draw something that looks nice. All right, so where do we begin? Well, I'm just going to start out by drawing an x and y axes. Here's x, here's y, or f of x will be here. And I notice I kind of shifted it to the right because I'm really only interested in what's happening at 0 and at 4. So, all right, let me start with these two pieces of information first. What is f of 0? Well, at 0, the function's value should be 2, and I put a dot there. So this is like college algebra. At 4, the function's value should be 1. Okay, those dots are for sure part of my graph. Now, this first part right here, this one. As I approach 0 from the left side, my function's y value should be getting close to 2. So here's 0, right? X is 0. As I come in from the left-hand side, my y value needs to be approaching 2. Well, 2 is where that dot is, right? So I can do anything out this side. It doesn't matter, because it eventually starts getting closer to 2. So that would satisfy this first part. Now, as I approach 0 from the right-hand side, I need to be approaching a y value of 0. So as I approach 0 from this side, I need to be headed to a y value of 0, which is flat. So how do I do that? Well, I'm going to put an open circle here, because that's where I need to be headed. And and that's coming in from the right. So I could come up here like this, or I could even bring it down here. I could wave it around. No, it doesn't really matter as long as it approaches 0 as I come in from the right. And that right there will satisfy the second condition. Now I left this like this because I don't know where it's going to go yet. I haven't figured out where this is going to connect to. But this next piece of information should help me. As I approach 4 from the left, I need to be headed to a y value of 3. So here's 4. From the left side, I need to be going to a y value of 3, which is up here. So I'm going to put an open circle here. That's where I need to head to. And coming in from this side, I can connect it in here like this. So that would work. And as I approach 4 from the right-hand side, I need to be headed to 0 for a y value. So here's 4. As I come in from this side, I need to be headed to 0. Well, that means I need to be headed here. I'll take this out. And then it doesn't matter which way I go out this way. You know, I'll bring it down this way, like that. That would satisfy all of the conditions. So like I said, yours could look a lot different. Let me show you a different one in a different color. Someone could have had this. Right? That red one would have worked. Okay? And there's an infinite number of possibilities here. The thing is, you don't want to leave like gaps here. You don't want to just like leave this empty. Come fill it in. So see if you can do 7, 8, and 9. All right, let me look at number 11, or sorry, number 13. Number 13. They give you limit x approaches 0 of sine x over x plus tangent x. Guess the value of the limit, if it exists, by evaluating the function at the given numbers correct to 6 decimal places. Ooh, okay. What in the world are they talking about? Well, look, if we try and plug 0 into this, right? If we just say, hey, what's happening at 0? So like, if we were to look at this as a function, f of x, and we were to say, all right, what's f of 0? Then you just replace everything with 0. You get sine 0 over 0 plus tan 0. And we all know sine of 0 is 0, and then tangent of 0 is also 0, and you get 0 over 0, and this is undefined. And that's why we're here, right? To try and figure out a way around this. So what we could do is, you know, we're trying to figure out on this graph, which I'm not going to graph it right now because I don't know what that looks like. We know that at 0, this function doesn't exist, right? It's not defined. But as we get closer from the left and from the right, it might actually be headed towards the same value or 2 different values. I don't know. So what I'm going to do, what they're doing here, they have written down here x equals plus or minus 1, and then they say plus or minus 0.5, and then plus or minus 0.1, and then they continue, right? So what they mean is this, by that notation. They want you to look at 1 and -1, okay, like this. And they want you to just figure out what the value of the function is at both of those points. So no, they're doing plus and minus because they want you to check from the left and the right. And then we're going to do this plus or minus, and that means we're going to get closer left and right, and then this one even closer left and right. And we're going to try and figure out if there's some trend here. All right, so I'm not going to do all of these. It's going to take too long. But what I will do is -1 and 1. So what would f of 1 be, and what would f of -1 be? I'll need my calculator. And I need to make sure that I am in radian mode because I'm going to be doing sine of 1, right? Sine of 1 over 1 plus tangent of 1. And we do not mean 1 degree, we mean 1 radian. So I am in degree mode. I'm going to have to switch to radian mode. And I'm gonna figure out what this is on my calculator. So I'm doing sine of 1 and 1 plus tangent 1. I get 0.329. And does it say how many decimal places? 6 decimal places. 0.3290327. I went too far, but that's good enough. Now I try the same thing with negative 1. I get the same answer. Hey, so I get the same answer. So that means at 1 I'm at let's say that this is 1 unit high. I'm at 0.329, somewhere around here on both sides. So now I go in further. Let me try these two. So f of 0.5 and f of negative 0.5. This is not a very efficient way to do this, but it's just to give you an idea what's happening graphically. So let me change this. I get 0.48 or 458 2093. Now if I change those to negative, I should get the same exact thing. I'm just going to double check it. Yes, I get the same thing. All right, so this gives me the same. So 0.48, so we're like maybe around here, and the same thing on the other side. Maybe it's headed towards 1. Don't know yet. Let's try, I can do this one now, but let me go down to the smallest one they have on this list, which was plus or minus 0.01. So I'm going to do that one in here now. .499. So when I do f of 0.01, I get 0.499983, something like that. So as I get really close, I'm like really close to 1 on both sides. So just by our table, like making this sort of table, I could say that this is probably going to 1. No, 0.5. Oops. 0.49. Oops, I wrote the wrong thing there. Not 1. Let's say this is 0.5. My graph's off a little bit. Here's 1. This is 0.5 right here. We were really close to 0.49999. So it looks like it's headed to 1/2. Sorry. Wake up. All right. But this is not a proof. I mean, this is not for sure. This is just getting us used to the idea of what we're doing again. We're coming in from both sides, trying to figure out what the function's doing. All right, so I want you to try and do the same thing for 15 and 17. I'm just going to write down for number 15. Just kind of help you get this set up. What you can do for 15, you're trying to find the limit as x approaches 0 of square root of x plus 4 minus 2 over x. And if you just double check real quick, if you try and plug 0 in here, 0 plus 4 is 4, square root of 4 is 2. 2 minus 2 is 0, so you get 0 on top and then replace that with 0, you get 0 on the bottom. So if you just try and figure out what's happening at 0, it's undefined. So what you do is treat this like a function, f of x, and then start moving closer and closer to 0. So I would do, again, like this same table. Come in, 1 and negative 1, positive 1.5 and negative 0.5, positive 0.1 and negative 0.1, and keep moving in towards 0, and just figure out what happens. Now I will say on number 17, you want to be careful because it's the limit as x approaches 1. Now that's different because here's 1. If I want to approach there, what I'm first going to do is start maybe here at 2 and at 0. So instead of using this, I'll plug in 2 and I'll plug in 0, and then I'll go halfway. So maybe 1.5 and 0.5, and then I'll go even closer. So maybe like 1.1 and what's right in front of that, 0.9. Hope that makes sense. And then just get it closer and closer, and just do maybe 5 of those until you can convince yourself what this limit is approaching. Number 19, that's really kind of an optional thing. Use your graphing calculator to try and figure that one out. Make sure you're in radian mode. All right, that should be it for the first section's homework. I hope that helped.